other K constant for equilibrium. It's just like KEQ for K of equilibrium, or KC for concentrations, KP was for pressures. Ksp is going to be the solubility, that's looking at a solid dissolving. Product as in multiply. So what you're saying is, if I had a solid that's not very soluble, we use these for solids that aren't very soluble, like silver chloride. For the most part, we say, well, we know that halides hide because they're small, so that means chlorine is insoluble. It's a halide with silver, mercury, lead. That's the small thing that we learned in class. Halides hide when they're insoluble with silver, mercury, or lead. So this guy we call insoluble, but the truth is it will dissolve to a small degree. So it'll dissolve and it'll come to equilibrium with some amount of silver and some amount of chloride ion. So these two actually are present, but in really, really small amounts. So maybe if I put some silver chloride in a liter of water, the concentration of silver would be something to the -5th. So that would be the molarity of the silver that could be dissolved. So the Ksp expression is just the K expression. We always write products over reactants, and we know that we leave solids and, oops, sorry, this is aqueous, solids and liquids out. So I'm going to put these aqueous ions in my expression. So Ksp is equal to the concentration of the silver ion times concentration of the chloride ion. And the reason Ksp works, the reason you can have this constant value, which is the product, or these concentrations multiplied, is that the more silver ions you have floating around and the more chloride ions you have floating around, the more likely they are to collide. And so they're going to join together and become a solid. They're going to precipitate. So we can only have a certain value that the concentration of this times the concentration of that can be equal to. Otherwise, they're going to start finding each other in the solution. They're going to start clumping up and making a solid. So Ksp is going to be just the same as KEQ, except for we always have a solid. So we're never dividing by something, because it's going to be products over reactants. Your reactant was a solid, you leave it out of the expression. So we're going to do the same things in these problems that we did for the KEQ problems. We'll always write our balanced equation. We'll set up an ICE table, an ICE table, the initial change in equilibrium concentrations. We'll plug in what we know, and we'll set up a K expression and plug in what we know. Whenever you're stuck, if you do those three things, you're probably going to figure out, I'd say you have like a 75% chance of figuring out what you can do next if you do those three parts. Let's see a problem. We have silver bromide dissolves at 25 degrees Celsius, or when silver bromide dissolves at 25 degrees Celsius, the concentration of silver is 5.7 times 10 to the -7th. We want to know what Ksp is for the silver bromide. So first I'll write my balanced equation. Silver bromide dissolves, it makes silver ion. And here's another halide, by the way. And it makes bromide ion. Okay, so that's my balanced equation. I'll set up an ICE table. I know I have some amount of solid. I don't really know how much. Initially, I don't have any silver or bromide. I lose 1 mole of this or X moles of this, and for every 1 mole of this I lose, I make 1 mole of this and 1 mole of this. So if I lose X here, I make X here, and I make X here. So that means at equilibrium, what I really care about from this whole table, all I care about from this table is that at equilibrium, these concentrations are equal because I make 1 mole of silver for every 1 mole of bromide. Okay, so that's my ICE table. I'm going to go ahead and plug it into my K expression. So I know that Ksp is going to be equal to these concentrations multiplied, the product of those concentrations. So the concentration of silver times concentration of the bromide. I leave silver bromide out of it because it's a solid. So now I go ahead and plug in and I say that I'm solving for Ksp. Ksp is going to be X times X, and X is 5.7 times 10 to the -7th. So that's going to be the value of each of these. So X times X is X squared, or 5.7 times 10 to the -7th squared. So I plug that in and I calculate my Ksp, and I'm going to get, when I round it to 2 sig figs, I'll get 3.2 times 10 to the -13th. So that's the Ksp value for silver bromide at that temperature. So let's see. Here's another one. This one's a little bit trickier because I don't have the 1-to-1 ratio. So here I have some lead 2 chloride is added to water. So PbCl2 is going to be dissolving. And as it dissolves, I'll make one lead ion. That's a Pb with a 2 plus charge. And for every one of these, I'll make 2 of these. So I'm going to make 2 chloride ions with 1 minus charges. Okay, they come to equilibrium. And when they're at equilibrium, I'm given the concentration of the lead 2 plus ions. So let's say if I had some solid, I really don't care how much because the solids are going to be left out of the expression. But I'm starting with no lead and no chloride. And for every X moles of this that I lose, I make X moles of lead. And I make 2 moles of chloride for every 1 mole lead, so that'll be 2X. All right, and then I know that my concentration of the lead is going to be 1.6 times 10 to the negative 2. So that's my X. My X is 1.62 times 10 to the negative 2. And I know that the chloride is going to be twice as concentrated as the lead because I make 2 chlorine or 2 chlorides for every 1 lead. So that's going to be 3.24 times 10 to the negative 2. Okay, so I have my equilibrium concentrations of the lead and the chloride. I'm looking for Ksp. I'll go ahead and set up the expression and then plug these in. So Ksp is going to be equal to concentration of lead times the concentration, I should have made these brackets, times the concentration of the chloride raised to its coefficient, so that's squared. Okay, so I can plug these in. Ksp is equal to this times this squared. So 1.62 times 10 to the negative 2 times 3.24 times 10 to the negative 2 squared. And when I plug this in to calculate my K, I find out, let's see, I get 3 sig figs because my only number has 3 sig figs. So I find out I get Ksp equals 1.70 times 10 to the negative 5th. And we don't have to use units. AP doesn't require us to use units for the K expressions. And one last one. So I have calcium carbonate. I actually care, this is the one that we care a little bit more about. If you're wondering, why do I care, what concentrations are going to be present before something precipitates? Well, you can think about coral or any shells, and they have calcium carbonate in them. So we want to know what concentrations need to be present in the ocean before this stuff can precipitate. Because, you know, if it dissolves, little animals lose their shells and coral dies. So we have Ksp for calcium carbonate is 3.8 times 10 to the negative 9th. What is the solubility of calcium carbonate at 25 degrees Celsius? I'm going to bet when you first see these problems, you read that and you just think blah, blah, blah. So I'll do what I always do. I'm going to write the equation, calcium carbonate. It's going to dissolve. It'll make one of these and one of these. So a calcium 2 plus ion and a carbonate ion. All right. And I know that if I start with some solid and put it in the water, some amount of it's going to dissolve. And I'm putting it in pure water, so I won't have any of this to begin with. And as I dissolve it, for every one of these, I make one of these, I make one of these. This is nice, at least now I know these concentrations are going to be equal to each other at equilibrium. So what I'm trying to solve for is it says, what is the solubility? That's saying, what is this X? How much of this dissolves? How many moles per liter of calcium carbonate dissolve? Okay, well, my expression is Ksp is going to equal the concentration of that times the concentration of that. So calcium ion times carbonate ion. I get to see that they're going to be equal to each other, and I have the Ksp value. So I can say 3.8 times 10 to the negative 9 is Ksp equals these guys, and they're equal to each other, so x times x, or x squared, and then x is actually going to tell me my solubility. So I will square root both sides, and I'll find out that x, which is the solubility, is 6.2 times 10 to the negative 5th. Okay, so that is the solubility of calcium carbonate.